Everybody, and welcome to another video on my channel. Today we will be talking about an overview of limits and calculus, which is going to be the bulk of the Intro to Calculus series, and we will be covering many of the topics covered in this video in more detail in the following videos, but this is just to give you a basic understanding. Now, we need to understand what is a limit exactly. So, a limit describes how a function's y value, or if we have like f of x is equal to something of x, that means what will that y value approach as the input approaches a point. So basically, let's say x approaches a point A. That means, and so what we're trying to figure out is what's the value of f of A as x approaches to A. Now the notation is limit as x approaches A, and we normally have the x arrow A on the bottom of the limit symbol of f of x is equal to a value L. And meaning means as x gets closer and closer to A, but not equal to A, fx gets closer and closer to L. Now, but not equal to is very accurate because we're first of all trying to find the value that it would be approaching this value. But sometimes, as you can see, it will be that value at that certain point. So we're kind of trying to find out the y value at a certain point, but also we can also try to figure out values that are approaching to that value. And now those are two slightly different things, which I will cover later on in this. This is an example. So let's say we have a problem and limit as x approaches to 2 as x squared minus 4 over x minus 2. Now direct substitution gives us 0 over 0, which is undefined. And as you see, now we're actually showing how it's different from direct substitution, because if we did substitute the value in, it gives us an undefined value. So we're trying to figure out the value as it would be approaching x is equal to 2. But the value would be the same as if you plotted it, but you're not directly substituting. That's the biggest difference between limits and direct substitution. But this limit exists. If you have tables, the values will approach y is equal to 4 from both sides. Now, the algebraic solution, basically using algebra to figure out the limit, is factoring, as we're revealing limit as x approaches 2, x squared minus 4 over x minus 2. If we factor that, that becomes x plus 2, and 2 plus 2 is equal to 4. So that really illustrates the main difference between direct substitution and really taking a limit. There is something called a formal definition of a limit, and this will be covered later in the series as well, and will probably be covered towards the end, as this is quite complicated. This is quite complicated, and this also is pretty foundational for derivatives. So, for the formal definition is, if we have a value epsilon that's greater to 0, there consists a delta which is greater than 0, such that 0 is less than the absolute value of x minus a is less than delta, then f of x minus L absolute value is equal to epsilon. Epsilon. So, now if we go back to this slide and we see the notation, A is the x value the point is approaching to, and L is the y value or f of x value that the function is approaching. So, if we go back to this slide, that means there's a delta greater than 0, such that if x minus a, the absolute value of x minus a is in between 0 and this mysterious value delta, then epsilon is greater than the absolute value of f of x minus 1. L. Now this is the formal definition and has ties to a lot of different things, and as I said earlier, yes, we are going to be covering this in another video, but it will be much later in the series. Now, for a visual interpretation, there you could say there is an epsilon band around L on the y-axis and an interval and a delta interval around A on the x-axis. Basically, what you're saying is on the y-axis, there is a range where epsilon is, and on the x-axis, there is a range where delta is. Now, for an example which could help clarify it even more is if you have f of x is equal to 2x plus 3 as x approaches 1, that means we have to take the limit of that. If epsilon is equal to 0.1, that means then delta is 0.05, and that ensures that f of x minus 5 absolute value is less than 0.1. Now, f of x approaches 1 is 5. Now 5 minus 5 absolute value is 0, and 0 is less than 0.1. There are a few basic limit laws that are pretty common, and it's really useful for just generally simplifying limits. So, if limit x approaches a of f of x is equal to L, and limit x approaches a of g of x is equal to m, then that means the sum as limit x approaches a of f of x plus g of x is equal to L plus m. The difference is the same thing except L minus m, and the product and quotient are the same rules. Now another way to show this is limit as x approaches a of f of x plus g of x is also equal to limit of x approaches a of f of x plus the limit as x approaches a of g of x. Now if that becomes L, if we substitute L on m, that becomes L plus m. And the same thing applies for all of the other rules. Now for the constant multiple rule, if we have c times f of x, that's equal to c of c times L, where c is a constant. Now, here is a quick example of using limit laws. Now, you don't really have to see this slide much. You can skip a little bit forward into the video where the next slide is. But it is a pretty quick example and could help explain this a little bit more. So, if we have limit as x approaches 2, x cubed minus 1 over x minus 5. If we use the quotient law, that means it'll be L over m. So the limit as x approaches 2 of x cubed minus 1 is 7, and the same thing goes for x plus 5. So the final result is we have 7 over 7 is equal to 1. Now, direct substitution property is for polynomials and many continuous functions, limit as x approaches a of f of x is equal to f of a. Now this is a very important rule, and I want you to remember something known as continuous functions, because this is probably the most important thing you need to know for limits, whether it's continuous or not, and this helps us figure out direct substitution and many, many more things. So that's basically all you need to know for the example. But if you had to take one thing from the slide, it would definitely be this direct substitution property. And in fact, you should bold this, italicize this. If you're taking notes from my video, please take this note down. This is going to help you a lot with understanding the concepts in the later part of this series. There are also things called indeterminate forms. Now, indeterminate forms is where some of the laws, especially the quotient law, start to break down. Now, what I mean by that is, let's say we have the quotient rule, but it's something over 0, like 0 over 0. Those limit laws don't really apply to these indeterminate forms, and sometimes this even means that this is violating a lot of laws, and sometimes this means that the direct substitution property doesn't apply, which means that the function is sometimes not always continuous. Now, commonly, this happens when limit approaches infinity or there is a denominator of 0. Now all these bullet points are all the indeterminate forms, and these are pretty easy to remember. Just know that basically if you have anything divided by 0 or anything with infinity in it, unless you have something like 0 divided by infinity, which is just 0, but anything with a combination of 0 and infinity normally, or just infinity in general, is normally an indeterminate form. Now, there are resolution techniques where you have factoring, rationalization, where you rationalize square roots, and some more algebraic manipulation and trigonometric manipulation. Now, where it says limit x over to 0, sine x over x is equal to 1. And this is something which we call a pretty special limit. And this is something we are also going to cover in a future video. There are also things known as one-sided limits. Now, what I've been mostly covering so far is two-sided limits, especially when it comes to examples where it says tables showing values approaching 4 from both sides, which is also very, very important that you need to know, because it can approach for both the left side or the right side, and it doesn't exactly have to be one thing or another. Now, the left-hand limit, normally you have a minus sign after the a to show that you're approaching a from values less than a. And right-hand limit, you have plus, so because it shows you're approaching a from values greater than a. Now, a two-sided limit only exists if the limit at 1 is equal to the limit at the left-hand limit is equal to the right-hand limit. Now, you might think that for all functions, not just a lot, that this is true. But this is pretty much only true for continuous functions. For functions such as piecewise that don't directly intersect, these don't exist, and there's pretty much only left hand and right hand. Now, one side limit example, and this is a quick example, and as you see, I told you in the last one, piecewise functions often don't always have a two-sided limit. Sometimes they only have left or right. So, for a piecewise function, let's say f of x is x squared if it's less than or equal to 2, or x plus 1 is if x is greater than 2. So, the left limit says that x from the left side is 2 squared, which is 4, because we're approaching it from the left side or less than the a value. And the right hand side, but it shows 3 because x plus 1 at 2 is 3, and because it says greater, that's the right hand side. Now, a conclusion is, since these differ, limit of x approaches 2 of f of x doesn't exist, especially the both sides limit, as the two values differ. Now, using one-sided limits is pretty much very common, either when someone is just starting out with limits, or if you want to draw conclusions about whether a limit exists. Or here's a special type. Here's of an indeterminate form limit where you have infinity or some form of infinity. So, what you have is a definition is when function values grow without bound. So, let's say we have limit as x approaches infinity of x squared, and that becomes infinity. Now, that's positive infinity, but negative infinity is also pretty much the exact same thing, except it's negative. Now, an example is where you have 1 divided by 0, because 2 minus 2 is 0, 0 squared is equal to 0, and 1 divided by 0 is equal to infinity. Now, limits at infinity is, first we have a definition, is we're examining functions as x grows very large, which is also kind of a form of infinite limits, but the difference is for infinite limits it can be anything as long as y goes, but for limits at infinity is actually just as x grows very large, and they don't have to always approach infinity for the y value. Now, there are 3 cases for polynomial functions, especially if we're dividing it. if degree of p, which is the polynomial in the numerator, is less than the degree of polynomial q, and if polynomial q is in the denominator, that means f of x is equal to 0. Case 2 is if they're equal, and that is the ratio of the leading coefficients. So let's say we have 2x squared plus 5x plus 1 divided by 3x squared plus 7x minus 10. The limit as x approaches infinity would be 2 over 3 since it's 3x squared, or if it was 2 over 5x squared, it would be 2 over 5. Now case 3, if degree of p is greater than degree of q, it's either infinity or negative infinity. And at the bottom is a quick example where it's the same thing, and it shows 3 over 2 because 3x squared and 2x squared are the same degree. And 3 over 2 is, well, 3 over 2. There are many strategies for finding these limits. One of them being direct substitution for continuous functions, which is the most basic form and which I've covered, and how this doesn't always work. Now, sometimes you need to algebraically manipulate it because it won't always be there by direct substitution. The third method is numerical estimation, where you use multiple tables of values to figure out whether it approaches the same value. This is often used for one-sided limits and piecewise values. Now, the fourth method is also pretty much used very commonly with one-sided limits and piecewise functions, which go together a lot. And this is graphical analysis, or really we're using our eyes or a visual inspection of the graph of the function. This is a very important limit of sine x over x as x approaches 0 and it approaches 1. Now, we're going to be covering how to solve this algebraically in another video, but this shows the last two methods, graphical analysis or even using a table of values, except this is only from one side. Actually, no, it's from both sides, but it still works. Now, as you see in the radians for the top row, that means we have negative 0.1, negative 0.01, 0.01, and 0.1. And as it approaches 0 from both sides, it approaches 1. And for the graphical analysis, it approaches that certain value 1 at x is equal to 0, even though the function is undefined at that point. Because if we approach 0, sine of 0, 0, divide by 0, well, 0 by 0 is one of those indeterminate forms we found pretty early, and it's the first one that's mentioned over here, and probably the form that you're going to see the most. Continuity and limits is another very important topic, especially this topic of continuity, and sometimes calculus books dedicate entire chapters or two just about continuity instead of a short summary of it. Now, there are 3 rules to make sure that a function is continuous. So, continuity definition is if a function f is continuous at a point a, if f of a is defined, limit as x approaches a of f of x exists, and limit of x approaches a of f of x is equal to f of a. What the third rule means is basically we can use the direct substitution property in order for this to be used. Now, there are different types of discontinuities, assuming it's not continuous. Now, the first type is a removable one, which is a hole, where the limit exists, but it's not equal to f of a, or f of a is undefined. A jump is if left and right limits differ, so the one-side limits are not the same. This is found quite often in piecewise functions, but there are a few which are quite continuous. And infinite, where the limit is infinite or there is a vertical asymptote. Now, derivatives is one of the main applications of limits, and there is a limit formula for the derivative. So, of course, the derivative definition is the instantaneous rate of change, and the limit formula for derivative is f dash of a, or you have the derivative of a function x at a point a, where limit as h approaches 0 of f of a plus h minus f of a over h as h approaches 0. What will this value be? Now, you normally are using algebraic manipulation to solve this, but as you can see, this is actually, in the example, this is actually quite used for very small limits and for beginner calculus students to understand the rigor of limits and how they can be used to solve derivatives. But as polynomials get more advanced and for different types of functions, we move on to the derivative rules. But it is very useful to use limits to solve derivatives, as it gives a groundwork for the limits and the derivatives and how all of that exactly works. And at the bottom is an example which I won't read over, but if you want, you can always pause the video and read over it. Limits are also used in integrals as the formula for an exact formula. So, the definite integral is also called accumulated change, not just the area under a graph, but that's also pretty much accumulated change. Now, it's defined as a limit of Riemann sums, where I talked about that in a basics to limits, basics of integrals video, where you would have a Riemann sum of each of the points and the length, which will be covered more in my actual calculus series where I talk more about this. But just know that you have a limit as n approaches infinity of all these Riemann sums. And in case you forgot, each of the Riemann sums is if you have those mini rectangles and add them over and over and over again. Now, of course, integrals have applications as in area, volume, work, and probability. That's about it. Thank you so much for watching the video. See you in the next one, and bye-bye.